In this lecture, we're going to understand the system calls for process management in xv6. Please refer to this URL for more details on this lecture series. So let us take a step back and see what is the process tree and how processes are created in xv6. So when xv6 boots up, it starts the first process, which is called the init process. And this init process then forks and creates the shell process. And this shell process is the main screen that you see when you run xv6, right? The shell process asks the user for commands and executes the command. So whenever you type in a command or run a program from the shell forks, spawns a new child. For example, if you say ls, the shell forks a new child, then runs the ls executable in that new child. And when the child has completed, the shell waits for the child to complete, reaps it, and then goes back to the prompt again. And this whole process repeats again, right? So this is how the xv6 shell and any shell in general runs user commands. So these are the main processes that are running in xv6 at any point of time. So note that not all commands will result in the shell forking a process. For example, some commands like cd should be implemented directly in the shell itself because you want to change the working directory of the parent shell itself and not of some other process. Therefore, such commands are directly executed by the shell without having to fork a child. But when the shell wants to run some other command where it has to exec, rewrite the memory image, then it has to fork a new process. So previous lecture has explained all of these basic concepts. And in this lecture, we are going to just understand and see these concepts in the form of xv6 code. So this is the main function of the xv6 shell that is started by init after the system boots up, right? So this is a very simplified version of a shell that you will see in real operating systems. So what this shell does is, of course, it will ensure that the standard input output file descriptors are open. That is this part of the code. And then it reads a command from the user into a buffer. And if this command is cd, then it will invoke the change directory system call. The shell itself will invoke the change directory system call. There's no forking and all of that. But if it is any other command, then the shell forks a child process. And in that child process, it runs the command. So this run command is basically calling the exec system call. We don't see the code here, but the exec system call is called here. And it forks a child, runs the command in that child via exec, and then waits for the child to complete. The parent shell process waits for the child to complete. Right? So this is how the simple shell in xv6 looks like. So now let us understand a little bit more detail about these system calls related to process management. So first, what happens on any system call? So all the system calls that are available to user programs in xv6 are defined in this file user.h, right? Here is a small snippet from that file. So this is just equivalent to the C library where system calls are defined, where functions that actually invoke the system calls are defined. So xv6 doesn't use the standard C library, therefore it has defined its own header file that has all of these functions. And this code can be seen from GitHub. It is not available in the PDF source code booklet that's put up on the web page because this is actually part of the user space code. It is not the kernel code. So if you write a user space test program in xv6, you will have to include this header library that has all the system calls available to you. So what happens when you call one of these system calls here, when you call fork or something? This system call is actually implemented inside the kernel. So there is a hook into the kernel. So then this file uses.s, this file defines all of these system calls, right? So whenever you make a system call like fork, what is happening is there is a hash defined that defines this fork as basically you put some number into some register and you call this int instruction, right? So what is this int instruction? We are going to go into a lot of detail about this in a subsequent lecture. For now, what you need to understand is this is a special trap instruction, which basically causes a jump into the kernel code. Okay. So you call int with some number indicating a system call. Then what happens is you jump into the operating system code and you go ahead and invoke the functions of the operating system that implement the system call. Right? Every system call is given a number. That number is pushed into a certain register so that the operating system knows which system call to run. Okay, so we are going to study this trap instruction in more detail later on. So don't worry if you don't understand this for now. All you need to know is whenever a user program makes a system call, there is a special instruction, the int instruction, which causes the CPU to jump into the kernel code that implements that particular system call. Okay, so all this int instruction is doing is jumping into the kernel code so that the operating system code that implements the system call is invoked. Note that system calls have to be implemented by the operating system. They are OS functions. They have privileged instructions. They are not like some regular function in a user space program that you have, right? So therefore, there is a special mechanism, a protocol to jump into the kernel code. So all the system calls that are defined in user.h are implemented this way using the int instruction. Now, in a subsequent lecture, we're going to understand how exactly the int instruction works. For now, assume all of that jump has happened. And now let us just look at the kernel code for these process management related system calls, right? Don't worry about how this jump exactly is happening for now. So this is the code for the fork system call inside the kernel. Okay, once again, we won't be studying the entire code here. We are only going to be studying a few concepts that we know now. And later in subsequent lectures, when we cover more concepts, we're going to go into more depth. We're going to revisit this fork function again multiple times throughout the course of this lecture series. So this fork is invoked by a parent that wants to start a child, right? The parent has called fork, and this fork will create a new child process. So what happens now? The parent has invoked the int instruction and it has jumped into the kernel and it is running this fork code. As part of this fork, what happens? There is this function alloc_proc. We will study it later. What this does is it allocates a new process. It creates a new process in the ptable array of xv6 where all the list of processes is present. A new entry is allocated for this new child process. And then the next thing we do is, the next thing the parent does is it copies all the state from the parent to the child. That is the memory of the parent. So the parent has certain memory image, all of that is copied into the child process. Exact copy of the parent's memory is made for the child process in this function copy UVM. We will once again revisit this function later on. Okay, and then the size of this new process is copied from the parent size because it's exact copy of the parent, right? It'll have the same size. Then the parent pointer is set correctly in this new process. Okay, and then the new process state is set to runnable, then so that the scheduler can run this process. A few other things are done. You know, the open files of the new process are copied from the parent. The name of the process is copied from the parent. All of this is done. Of course, a new PID is allocated for this child. When you did alloc_proc, the structure that was returned to you had a new PID. You're going to use that. And the trap frame, this is another data structure in the struct_proc. We're going to study about this later. That is also copied from the parent. So you're allocating a new entry in the ptable and copying various things from the parent into the child. And finally, the parent process returns with the PID of the child. And for the child process, you clear some register somewhere. You set it to 0 so that the child returns with a value of 0. Right? So this a piece of information actually has the return value of the child. Why is this the return value of the child? We are going to study later. But so I hope this entire thing is clear. A new struct proc has been allocated for the child. Various things have been copied into the child's memory image, and trap frame and various other data structures in struct proc have been populated. And the child has been marked as runnable, so that the next time the scheduler loop runs, it will find the child and go ahead and run it. And the parent returns with the PID of the child. So the fork system call returns in the parent with the PID of the child. And you clear some value in the struct proc so that the child returns with a value of 0. So this is the code that is run by a parent when it does a fork to spawn a child in xv6. Next is the exec system call. I'm not showing the code because it is quite complicated, but I'll just explain briefly what happens in the exec system call. You can refer to the source code PDF for the full code snippet. So what happens in exec system call is a process has certain memory image. It has code, data, stack, heap, everything, right? There is a heap, there is a stack, whatever is there in the memory image of the process. In xv6, you actually have the stack first and then the heap. We will, of course, study this later. So all of this is erased out and a new copy is put up, right? All the code data that is there for the old, in the old memory image, all of that is erased and a new memory image is created, right? So the new executable is copied into memory, a new stack, new heap, everything is created for the process. And the new page table points to this new memory image, right? So there is an old memory image, you discard that and you create a new memory image. That is what happens in exec. And the process will then start to run this new code that is there in the new memory image. So that is what the exec system call does. Now this is the exit system call. A process that wants to terminate will call exit. What happens in exit? Again, we will revisit this function later on, but for now, a few important things to note are a process cleans up all its state. If it has any files open and things like that, it will clean up all of that state. And then if it has any children, it will reparent those children to init. It will set the parent of its children as the init process so that init can adopt all of those children, right? And if its parent is sleeping, it will wake it up so that the wait system call in the parent can return. And the exited process will set its state to be zombie and it will invoke the scheduler. It will say, I don't want to run anymore. I am a zombie. I've cleaned up some state. Please take me out of the CPU. I don't want to run anymore, right? So that is the exit system call. What it does is it cleans up some state. Note that it does not clean up all state. All state is cleaned up only when the parent reaps the dead child. That is when the complete cleanup happens. For now, some state is cleaned up. It takes care that all its orphans are adopted by init, and it marks itself as zombie and invokes the scheduler. This is the code of the exit system call. This is just a high level overview. We will return to this later on. Now this is the wait system call. A parent process that has spawned a child should periodically call wait so that once the child has terminated, the wait system call will clean up the state of the terminated child. So what is happening in the wait system call? The parent is looking through the process table, seeing if any of these processes are its children. If any of the process is its child and the process is a zombie, right? You're checking if the parent, if I am the parent of that process, and if that process in this process table is a zombie, then I have found a dead child. Here is all the cleanup that happens and the wait system call will immediately return. Okay, so you clean up all the state of your dead child and you return with the PID of your dead child. On the other hand, if you do not find a dead child, if you have children but they have not yet died, then you will wait. You will call this function sleep and you will wait. Okay, if a dead child is found, you return. If no dead child, then you sleep until a dead child comes up. So this is the wait system call in xv6. So this is a summary of all the system calls that we've seen in xv6 that pertain to process management. The fork system call, when a process invokes the fork system call, a new child is created, a new struct proc is marked as runnable in the ptable. The child's memory image is initialized. It is basically a copy of the parent's memory image, and various things state from the parent are copied into the child. And the child process is set to be runnable so that when the scheduler runs next, the child is scheduled. The exec system call rewrites, reinitializes the memory image of the process. The user space, code, data, stack, heap, everything is reinitialized so that a process can, when it goes back from the system call, it can run new code. The exit system call, a process marks itself as a zombie and gives up the scheduler. Wait system call, whichever process was marked as zombie, whichever child has been marked as zombie, that is found, and the parent cleans up its state and returns. And if no child has died yet, the parent will wait for the child to die. That is why the system call is called wait. So we've seen a rough implementation of these system calls in xv6. We will study them in more detail in subsequent lectures.